And please join me in welcoming Alec. So Alec Koppel is an AI research lead, senior scientist at JP Morgan AI Research in the Multi-Agent Learning and Simulation Group. From 2021 to 2022, he was a research scientist at Amazon within supply chain optimization technologies. From 2017-2021, he was a research scientist with the US Army Research Lab in the Computational and Information Science Directorate. He completed his master's degree in statistics and doctorate in electrical and systems engineering, both at the University of Pennsylvania in 2017. Before coming to Penn, he completed a master's degree in system science and mathematics and bachelor's degree in mathematics at Washington University in St. Louis. He's a recipient of the 2016 UPenn ESE Department Award for Exceptional Service and awardee of the Science, Mathematics, and Research for Transformation SMART Scholarship, a co-author for the Best Paper finalist at the 2017 IEEE Asilomar Conference on Signals, Systems, and Computers, a finalist for the ARL Honorable Scientist Award 2019, and awardee of the 2020 ARL Director's Research Award in Translation and Research Challenge, a 2020 Honorable Mention from the IEEE Robotics and Automation Letters, and mentor of the 2021 ARL Summer Symposium Best Project Awardee. His academic work focuses on approximate Bayesian inference, reinforcement learning, and decentralized optimization. He has worked on applications spanning robotics, autonomy, vendor selection and sourcing, and financial markets at various types. So please join me in welcoming Alec.
She said it was all one slide deck.
Let me see. Is it here maybe? It's a different slide, right? I think it's a PDF somewhere.
Working. Okay. Thanks very much for that nice introduction. Today is a talk, this is a talk about model-based reinforcement learning and why I think it's a salient class of algorithms for reinforcement learning. This is joint work with several co-authors at University of Maryland and Princeton and the US Army Research Laboratory. So I think I can roughly skip over the basic problem setup of reinforcement learning. The basic notion is you have an autonomous agent. It traverses a state space. It selects actions. For each action selected, it receives a reward and transitions to a new state according to some Markovian transition model. And there's a lot of recent technology spanning academia and industry and so forth that are using this basic framework. As the previous speaker pointed out, a lot of state-of-the-art model-free or model-based algorithms require a huge number of queries to a generative model in order to generate trajectory data so that you can estimate the cumulative return for a given policy and then execute updates. And typically in these papers you see something like performance improvement plots, where on the x-axis you're going to see either training epochs or evaluation on test trajectories, and on the y-axis you're going to see an estimate of the cumulative return for a given policy at that time. And so, this is from the DQN paper, and the main point to note is this x-axis is representing millions of training examples. in some cases even more for language models. And so that's for like value-based approaches, but the story is very similar for policy-based approaches like PPO, TRPO, and so forth. And so, you know, the main point is like, no matter which value-based or policy-based approach you go for, you tend to see like high variance of the cumulative return over the course of training, and like potentially millions of queries to a generative model in order to have like your policy converge to something meaningful. And so that's kind of like a huge gap between like experimentally what we see and theoretically when we talk about like optimal sample complexity. And so that sort of like begs the question, should we spend more time building good simulators so that we can converge more quickly? Should we spend a lot more time on model calibration? So there have been colleagues in my group at JP Morgan who have been developing like market simulation engines, and there's some papers about that recently. But as we try to go, let's say, towards like actual use of these things, there's a lot of skepticism about using these kind of simulation engines on the one hand. On the other, when we actually train in a simulation engine, we don't know if we're actually solving the quote like real problem, and like what is like a good kind of like conceptual framework to study convergence when we're training a policy on a simulated problem rather than a real problem. So we can talk about the convergence theory of model-free or model-based methods when they run in simulation. How do we actually know whether that policy has converged, if it's only converged on, you know, this synthetic problem? So this kind of sim to real gap is not well encapsulated by a lot of the like notions of sample efficiency that are floating around in the literature because of the sort of like assumption of access to a generative model. So like that's the basic point. And I just want to comment that like if we're going through all the trouble of building a simulator, shouldn't we try to like use it more explicitly for the policy optimization and try to talk about the convergence of our algorithm in terms of both how it builds the simulator and how it learns the policy? And so I think like model-based and Bayesian reinforcement learning are a little more attractive from this perspective because they sort of unify the question of what is the merit of the simulation engine that I'm building and the policy that I'm learning, and sort of like one common like quantifier of sample complexity, which is a bit different from just talking about you know, convergence of the policy gradient norm or the cumulative return. And they talk about also what is the convergence of an underlying like model as well as the policy that you're learning. And they formalize it using something called Bayesian regret, or I think there's a way to interpret the performance criteria that model-based reinforcement learning algorithms use, which is something called Bayesian regret, as unifying these two things. Okay, so what does Bayesian reinforcement learning do? Well, it tries to use the model more explicitly over the course of training. But there's like a lot of possible ways to use your model more explicitly over the course of training. You know, you could talk about like representing uncertainty inside Q-learning or inside a policy gradient algorithm. And there's like a lot of different heuristics for trying to like represent uncertainty in model-free settings, but mostly they don't have any sort of like conceptual basis. I would say they're kind of like anecdotal evidence. The ones that are more sort of like rigorously substantiated are like model-based Bayesian reinforcement learning algorithms. And so what they do is they maintain a posterior distribution over the rewards and over the states at each time. And then they talk about the convergence of those posterior distributions sort of like jointly with the question of like convergence of your cumulative return or policy. And so there actually have been, just like, they are a component of some of the more successful RL use cases in the real world. Okay, so yeah, there's a laundry list of potential alternative ways to use models in reinforcement learning, but the ones that I really want to talk to today, and I didn't realize that Dan Russo was going to be in the audience, so several of your papers are going to be called out as inspiring this work. What we're going to be talking about today is a class of ways to make posterior sampling or Thompson sampling, which is sort of like classic multi-arm bandit algorithm work in the MDP case, and ways to make it work for potentially continuous states and actions, or like beyond the tabular setting, and ways to make it explore more efficiently. And in that way, it will sort of like bring together this question of what is the convergence of my like model that I'm calibrating as well as my policy. Okay, so what's posterior sampling in a reinforcement learning? So there's some like technical, can't see the laser. Make it the mouse cursor. Okay, that's also gone. Yeah, so there's some technical preliminaries we need to formalize. Basically, you have a state space, an action space, a reward function, a transition model, a horizon, some upper bound on the reward, and we assume that we are going to we still need to like get access to trajectories from the states and rewards, but we're going to start with like an uninformed prior, and then we're going to define a value function, which is in the usual way with expectation over the transition model conditioned on a policy, but now we're also going to maintain a posterior distribution over states and rewards, and we're going to compute expectation with respect to these distributions as well. So that's going to sort of define a sort of Bayesian value function. And then the notion of Bayesian regret is just the difference between the value function associated with the optimal policy and some particular policy. And so I just want to comment that Bayesian regret is very similar to like vanilla value function suboptimality, except you have these additional expectations over like a posterior over rewards and states. Okay, good. Right. So how does posterior sampling or Thompson sampling work? The basic notion is you like time k, you would like sample from the true MDP in the form of like some trajectories. You'll fit some transition model. A lot of the earlier works fit like either like a Gaussian model or like a multinomial in the tabular case, and then you'll have a distribution over the value function that you represent as a multinomial or something. You'll compute the argmax of that value function, and then you'll sample to get the policy, and then you'll sample an action from the resulting policy and then repeat. So this framework has like a pretty like rigorous like theoretical backing in terms of like some regret analysis, but that kind of only works out so I say before we go into the theory, let's just talk about experimentally like posterior sampling like works very well for some like moderate dimensional problems. So I think it's it's the red. So basically like trying to estimate the transition model and then do model predictive control or like argmax of your value function with respect to the like the posterior value function under that estimated model, like works very well experimentally under some in some simplified scenarios, and even it works well in continuous control environments, but there was relatively less theory for that, and so what I'm saying is like to go from sort of like tabular settings to continuous settings, people typically need to make some very strong assumptions on like the transition model and the value function, certain like smoothness assumptions, and you have no idea how they affect performance. That's one thing, and the other is in order to actually like evaluate this posterior. Yes, so in order to actually evaluate this posterior, you see that you have to like keep track of this like trajectory data set at each time. If you use a certain class of simplifying assumptions for the posterior representation, then you don't actually have to track the full history, but yeah, in continuous spaces, it's not clear that you can actually do that unless everything's Gaussian. Right. Okay. So the question we want to pose is how can we make posterior sampling, which has like a pretty rigorous regret analysis in like tabular settings or bandits, work for continuous spaces, and then we'll talk about how can we further improve that in terms of exploration. So it's like the scope of the talk. Right. So as I mentioned, like depending on your choice of the posterior representation, you may have to track the full history of your past trajectories, unless everything's Gaussian in continuous space. This is true. So the first thing we're going to say is like, well, can we suppose that the posterior over rewards and states belongs to a certain mixture family, and then sort of like judiciously track the history so that we can obtain a good enough estimate for achieving good policy optimization, despite, in general, the complexity going to infinity. So we'll talk about ways to do that. So the first question is like, how should we do that? There's like a lot of different potential ways. Like for those familiar with autoregressive models, you would just keep like a fixed memory window, but there's no way to show that will actually converge to the true underlying posterior. So the thing that we were able to do, instead is say, well, let's suppose that the posterior belongs to a mixture family. Let's try to judiciously track which past trajectories are actually important for convergence. And if we develop this active set carefully, then we will still obtain, like if we choose this active set effectively, then we can still achieve sublinear regret with respect to the underlying policy optimization. Okay. Let's skip, or so let's go to exactly what's going on here. So if you take the posterior sampling algorithm we had before, and we say, okay, now we're not going to make any assumptions about Gaussianity or multinomial, just general mixture family. And so because of that, you're going to have a situation where you need to track all past trajectories. Well, we need a way of saying, well, I only want to track or I only want to retain the subset of past trajectories that are statistically significant in some sense. So you can do that by defining a certain like thinning procedure with respect to a statistic that tells you how important that trajectory is for your policy optimization. And because it's in a mixture family, specifically associated with a certain reproducing kernel Hilbert space, that's a mouthful, but basically it's similar to kernel regression. You can like evaluate distances in closed form. So I don't want to get into too many of the details. I just want to comment that there like, is a statistic that makes the evaluation of this of the importance of past trajectories tractable in closed form, and it's coming from approximate Bayesian inference. The basic idea is that you can compute the integral probability metric between two distributions in continuous space in closed form under some like smoothness assumptions. But whereas I said before, in general, like model-based RL has these like smoothness assumptions on value functions on rewards, which are difficult to verify. So what we're saying is like, well, now we don't need to make those assumptions. Let's instead make them dependent on some hyperparameters of our kernel that we can actually calibrate algorithmically. So now we don't need to make those assumptions. We can just, directly tune them. Okay, so that's what's going on. I want to skip through that just to point out that like as a result of this like way of tracking past trajectories for what's important now, we can make posterior sampling work in a computationally efficient way in continuous space. And at the end of the day, we could provide the first like algorithm to achieve sublinear regret for posterior sampling without too many smoothness assumptions on the value function that is going beyond simple like tabular spaces. And the reason you need tabular spaces in earlier work is exactly because of this parameterization complexity. So yeah, the point is like if we want model-based RL to work in continuous space, we need to calibrate our simulator or our posterior representation of the state, and that's what we're able to achieve by making these like very specific assumptions on the representation of the posterior and over the reward and state in posterior sampling. Great. So, but the title of this talk was actually something different. It was, or actually before I get to that, I'll just say experimentally this works very well for allowing posterior sampling to scale up to continuous spaces. And in particular, you can talk about what if you use vanilla PSRL as compared with this like thinning procedure, and we are able to observe like huge efficiency gains in model complexity. And so therefore you can like run it for many more training steps and see that you have like effective convergence that is like occurring much faster than a lot of the model-free methods. And I think so that like provides some like encouragement and trying to talk about both the convergence of your like simulator or like let's say the transition model that your algorithm is building together with the convergence of your policy can lead to like very practical like improvements in performance where we need to wait like much less time to obtain like a reasonable baseline performance. So I think I'll pause there for any questions because I've maybe gone very fast.
What's the underlying experiments? What's the data you're using to sample?
Oh yeah, okay, so this is a few different experiments. This is Mujoku, Cartpole, Pusher. Later we did experiments with like deep sea environment and a few other kind of like hard tabular settings as well.
So you experiment on financial data?
Yeah, I'm not, I think I'm not allowed to talk about that in the actual presentation, but yeah, during the coffee break. Yeah, that's a great question because it's important to note that Bayesian regret is only talking about convergence with respect to the expectation under the posterior. So we don't actually know whether that is like the truth unless you have some like operating hypothesis that like the posterior with infinite data is going to converge to like the correct thing. So that I think that's like a well. That's a good question that actually like perfectly segues to what I am going to talk about in like the second half of this talk. So thanks for that. One more question.
I wonder whether you know each new kernel and therefore function of each model, or you would also need to estimate them.
I'm not sure that I totally understood the question. Like there is a true underlying transition model, and then at each step, the algorithm is like doing a series of like maximum a posteriori updates of with respect to that model.
So the transition kernel you know
it's not known, but you can query it for trajectory data. Okay. Right, so we haven't said anything about to explore efficiently, and that could lead to scenarios where convergence in terms of Bayesian regret doesn't actually lead to converging to an optimal policy. Sort of like in layman terms, what that could mean is like if the algorithm's like beliefs are calcified or like hardened with enough data, but maybe the data that you have is somehow still having some like persistent bias, maybe related to symptom-to-real gap, or just the fact that you didn't explore enough in your data set, then Bayesian regret actually won't explicitly capture this phenomenon. And so you can actually observe that this would happen if in some like explicit way that's like kind of poetically illuminated in this like Deepmind deep sea environment. I think there's like a cousin to that environment called the river run environment, but basically they look like very long, almost line graphs with a very high probability near one going in one direction and probability near 0 of going back, and there's only a reward at like one of the states, so or some very small fraction of the states. So somehow this is like a pathologically sparse environment, and many algorithms get like stuck or don't find an optimal policy in this environment. So if you take Q-learning, it will achieve linear regret for that type of environment, meaning that Q-learning like never finds the optimal policy. There are other examples that have like similar pathology to Q-learning, but even if we take what I just spent a while, posterior sampling, I just spent a while extolling its virtues, but it also tends to get stuck in these kind of sparse reward environments. And just to give a little editorial on like the financial implications of sparse rewards. Sparse rewards can be coming from, let's say as like a model can be coming from maybe the fact that like your environment just doesn't like model how your reward depends on things you haven't seen. So at least like that's how it's typically thought about it, as a sort of like game theoretic like reinterpretation of why would you not observe the reward that you're hoping to see. So that's sort of like why we care about it in some of the financial applications. But so then the point is like, if you have sparse rewards, then Bayesian regret is not really capturing what, or it's not like a very effective notion of convergence, because yeah, it doesn't have any notion of like coverage of the state space. Right, so you can put this like more quantitatively through some notion of information-theoretic regret, which I'll formalize in a moment. But let's just say for that kind of, for like a certain tabular environment, let's say you have like two different policies, and like let's say the brighter orange or peach color are like higher probabilities of exploration, so unnormalized probabilities, and the more like raspberry fuchsia color is the lower probabilities, but then the reward is at the star location. These like two different policies will have the same Bayesian regret according to, even though they have a quite different like experience in terms of like what trajectories they prioritize. So yeah, there's no notion of like how much coverage does one of these algorithms like achieve over the course of like its learning process. And so because of that phenomenon in both Bayesian optimization, and I think maybe 15 years ago there's a paper from Andreas Krauss, but there's also been more recent work from Russo talking about information theoretic regret in bandits, that is like directly pertinent to this discussion, because they say, oh, actually Bayesian regret like has this decomposition in terms of let's just say there's an expectation of the optimal information, or let's say of the information gain under some optimal policy, or sorry, that's information ratio. I can't see this laser. This is the information gain term, and this is like an information ratio term. So this, the second term, or sorry, second factor on the right-hand side is sort of like capturing how much coverage is in your data set. And so what it's saying is like, actually there is an ordering in terms of how much data your algorithm like processed. And if we only try to like bound this according to some like factors that depend on the state space and cardinality and whatever, which is like maybe possible under some statistical assumptions, then we end up with a sort of like biased understanding of how much does our algorithm actually like understand. Yeah. Oh, okay. That's why that was right. So so what information-directed sampling algorithms do is they basically take the step in the Model-Predictive Control step in posterior sampling, and they normalize by this information gain term, more or less. And they define this quantity called information ratio, which is nothing more than the Bayesian regret in the numerator, and then there's like an information gain term in the denominator. And the reason that you want to define by this information gain is because it appears in the right-hand side of the previous expression. So now what IDS does is it seeks not only to minimize regret, but also do this like mutual information maximization. And that's like experimentally attractive because it says, I want my like model to be as good as possible in the limit of infinite data, but also I want it to cover as much information. I want it to do so in a way that's like making sure that its data set like contains enough information. Right, so I think it's like theoretically attractive, but the problem with that is like numerically to actually evaluate the information gain there, you typically need to like surrogate it by Pinsker's inequality that like replaces it with a posterior variance. And like whether that's valid depends a lot on like Gaussian assumptions, which as we were saying before can be like very, very limiting because you know, in various environments, like say your trajectory data is coming from a few different like market regimes, or then you know, you're not gonna have Gaussianity, you're gonna have a mixture family. So just replacing this with posterior variance can be very limiting. Let's see. So there's some like technical details. I just want to talk about like what is IDS doing in terms of its exploration incentive at step K, and it's basically regularizing by the gap between the posterior at time K and some and its like expected value, roughly. That's what the variance is telling you. But it's not like directing you especially towards the quote like optimal model. So, so in some sense, it has the right objective function, but its evaluation through its approximations is like not actually a directed exploration. So what we wanted to do is try to find a way to like evaluate some closer approximation of this mutual information that works for a general mixture family. And so you can actually use the machinery of kernel methods to make that work out. Basically, as I was saying before, if you replace information gain with an integral probability metric under some assumptions about the mixture family class, then it's actually possible to like evaluate this integral probability metric in closed form. So yeah, you need to assume basically that your mixture family belongs to something called the Stein class, and then you can compute this using something called the kernelized Stein discrepancy. The details are like not that important. It's a formula that like one can go look up. But eventually you can, rather than replacing information gain with posterior variance, you can replace it with this like Stein kernel evaluation of your past trajectory data, which like allows you to evaluate distance between mixture families. So it's like a much more like fine-grained notion of information in your data set. Okay. So the point is it's like closed form and tractable. And so then what we're calling Stein information-directed sampling is just an algorithm that replaces this mutual information with this kernelized Stein discrepancy, which we eventually call like this Stein distributional gain, right? So this was our ICML paper from last year, and the main point is that it resolved the computational intractability of estimating mutual information, and it allowed for, in a sense, a true directed exploration. And there's some like theoretical results we have in this paper that show that while we couldn't achieve like the tightest possible dependencies on state space and action space cardinality, we could match in terms of the horizon, and we were allowing this algorithm to operate with a much more general parameterization of the posterior in the setting. So then, like experimentally, the algorithm we're calling steering. There's the S is for Stein, and there's some other, you know, there's some other words in the acronym. What we could observe is that through this notion of directed exploration, you achieve a much sharper and like faster convergence in terms of Bayesian regret, and you can have like a more like granular understanding of like what directed exploration is, because like the convergence criteria is like explicitly trying to separate how much coverage your data has over the course of training. And yeah, there's like some other experiments that I punted to appendix slides, but yeah, these are experiments on several like benchmark environments showing that directed exploration can help a lot during over the course of training. Yeah, so I think with that I can conclude. I think the main point I wanted to make is like a lot of the convergence theory we have in reinforcement learning around sample complexity is sort of like untethering the question of like, is my model well calibrated from has my policy converged? Through model-based RL algorithms, we can try to bring these two questions back together through Bayesian regret and like related questions. But then as soon as you go down that rabbit hole, you have scalability problems with respect to your posterior distributions unless you make several simplifying assumptions that may or may not be practical depending on the application. So we try to make these algorithms scale more effectively in continuous spaces, as well as like provide a way to approximate mutual information effectively for exploration. So I think, yeah, there's forthcoming work in this ICML about how this Stein information can be used for pessimism in offline RL, but I think there's a lot of other ways that it could be extended, especially with respect to the evaluation of confidence sets in bandits and other problems where exploration bonus is helpful. So with that, I can conclude, and here's some references.
Thank you so much, Alex. Any questions for Alex?
How difficult is it to do the posterior sampling step once you have all of your data?
Well, that again, it depends on the modeling assumption for the Gaussian. Yeah, exactly. This was an appendix slide.
Yeah, I was going to ask, so are you assuming some kind of nice parameterization there?
Yeah, so I would say a lot of the earlier work was assuming either Gaussian in continuous space, or in discrete space they would look at like multinomial or Dirichlet. So we're trying to get away from that by allowing it to be belonging to a general like mixture family associated with these like reproducing kernel Hilbert space, but then you can't just allow it to be any space like that, because then you can't evaluate mutual information and several other important statistics. So we needed to make some assumption that the distribution belongs to the, quote, Stein class. And I can go way back to where this is actually required. I definitely glossed over that. Actually, no, it's here. Right. So when you have this, when you need to evaluate the integral probability metric between two different elements in it, RKHS, you can't do that in general. So the Stein class allows you to compute that in closed form with the one sample test. So that's another version of a smoothness assumption, but I would argue it's much less restrictive than saying the value function is globally Lipschitz. At least experimentally, it seems to be less restrictive.
Hi, regarding the actual training time, compared to model-free algorithm, this posterior sampling LL takes much more time to train, or it's about the same, especially, for example, in the case of the simple Mujoko Katapult kind of environment?
Yeah, I think I don't have the apples to apples numbers right off the top of my head, but I do want to point out that, yeah, exactly. We ran these for some number of iterations to achieve X percentage performance relative to the baseline. I think all those tables of numbers are in the paper, but I don't have them off the top of my head. The thing I would say is Q learning for some of these sparse reward environments was in some cases failing to converge completely. So we didn't want to we're trying to be very nice about the fact that it wasn't working at all.
Okay, thank you.
You mentioned spending more time modeling at the initial portion of the talk, and I'm wondering, for such a complex environment, and also let alone one where your agent is going to be has closed loop feedback into the environment, is modeling or improving the model almost a futile endeavor, just given we can always spend more calories improving the fidelity of a model, but some of these are just unknowable. So I just wanted to get your opinion on that.
Yeah, I think my point is we should try to ever further refine the model, and that the definition of convergence of our policy has to include a term which is handling our model calibration error. Otherwise, we're converging only to a surrogate problem. So I would claim that those two questions need to be pushed into the same question, so that the model calibration can continue. Yeah.
I was wondering, how does the result rely on the MPC oracle? Because, for example, you mentioned MPC as part of your algorithm, but for MPC, let's say you have to predict for a certain window. For example, how does the result rely on that, and how much does it rely on the fact that how well should I solve this optimization problem at each round? I seem to not be able to see that yet.
Yeah, that's a very fair question. So. Yeah, a lot of model-based RL, and we are no different, is restricting focus to episodic settings. So then, this MPC, this MPC is estimating value function with respect to that horizon, but it's not using additional trajectory data queries. Actually, it's simulating rewards and states from the current posterior distribution. So it's sort of has that like internal belief model to evaluate this argmax rather than doing like a separate Monte Carlo rollout. So in that way, it's dissimilar from how reinforce works. And I think a lot of the sample efficiency gains are because of that.
Hi, very interesting talk. A quick question about the numerator and the information-directed sampling. I think there's some kind of expectation of V star minus maybe V of the chosen action. Just curious, how do you approximate it in practice? Do you like Thompson sampling and then take an average, or?
Yeah. Okay. Yeah. This expectation of this quote, like optimal information ratio.
Yeah.
Yeah. That's actually a great question. In practice, it cannot actually be evaluated, but I think it's like a useful concept for helping to decompose Bayesian regret into things that can eventually be made tractable. So yeah, I think the optimal information ratio indeed depends on like the information gain of the optimal policy and the Bayesian regret of the optimal policy, and you don't know what these are. So I think that's like a very good point, but it's like actually used to derive tractable algorithms in practice as a sort of like intermediary step. So in that way, it has a lot of use.
Okay, thank you. Regarding to the environments with sparse rewards, could IPM method be related to inverse reinforcement learning to estimate the reward function during the training using a kind of teacher-based sampling or examples?
IPM. Integral probability metric. You're talking about how to fit an unknown reward function or distributional model? Yeah. Yeah, this seems doable because normally in like inverse reinforcement learning, you are looking at like divergence to like a prior distribution. So I think like for sure you could like replace that with other distributional metrics and then maybe come up with like a more descriptively rich parameterization and then like use, for example, Stein information to like make that computable. That seems like a promising, yeah.